Welcome to Electronic Devices and Circuits Lab. In this particular video, we are going to learn how to obtain the hybrid parameters of transistor using the experimental setup and how it can be determined by the graphical procedures. So basically in this lecture, I'm not going to talk about the what is hybrid parameters because it is a part of theoretical discussion. So I will be just discussing how this can be determined using the graphical procedures. So first of all, as we know that in case of transistors such as BJT bipolar junction transistors, it is normally having three different terminals. Okay, so these terminals named are base, collectors, and junction collector and emitter. Okay, so these are the three different terminals, and we already seen that two of them can be used in the input loop and other two can be used in the output loop. So one of the terminal is normally common. Okay, so one of the terminal will be common in input loop and output loop. So the terminal which is common to this both input and output loop is normally called as common terminal, or it is referred as common emitter configuration or common base configuration or common collector configuration. So here you can see that we are having this emitter terminal. So if we connect the circuitry in this loop, okay, and some input will be applied here. And again, we can complete the circuit, we can connect some output at this point, and then we can basically make a two-port parameters, right? So in this case, the two ports that will be used for input is base and emitter, and another two port that will be used for the your output, taking the output will be collector and emitter. So here is the example of your two-port network. Okay, so here we have these two terminals at the input side and another two terminals at the output side. So normally this is the basic expression of any hybrid network. If we have any two-port network and its equivalent hybrid parameter will be given by this particular equations. So normally we are having four different parameters: one input current, one input voltage, another input current, and so one input current and another input current and input voltage. Another set of parameters will be your output voltage and output currents. So normally in this case, we will be taking two different parameters as an independent variable. For example, here you can see that we have taken IE. Okay, this IE, II is actually your input current, which is we have taken as the independent parameter. Here we have taken V output as the independent parameter. So based on this two independent parameter, input current and output voltage, we are calculating the input voltage. Okay, so it is a dependent parameter Vi that we have to calculate. Similarly, we are keeping this output current. Okay, this output current as an independent variable, and based on this two, this is your dependent variable I output, and based on this two independent variable I and V output. So this will be giving you this particular output. Okay, so this way we are actually choosing two of them as an independent variable and we are calculating the other two. So in that connection, we are having several parameters here. You can see it is written as H11, H12, H21, H22. So these are the hybrid parameters that we actually have to calculate. Okay. So basically, you may find that these parameters H11 can be calculated as the ratio of V input upon I input current by keeping this V output equals to 0. So this V output, if you keep it equals to 0, then we can calculate this ratio. Similarly, you can calculate other values H12, okay, by keeping I equals to 0, we can calculate this ratio V input upon V output. So that will be giving you H12. Similarly, you can see this H21 and H222. Okay, this way we can calculate this different hybrid parameters. Here you can see this H11 is actually called as input resistance, and normally it is defined as HI. Okay, in this circuit. Okay, here you can see this is defined as HI. Similarly, H12 it is called as the reverse transfer voltage ratio. It is denoted by HR, and then H21, which is forward transfer current ratio, which is defined as HF. Okay. Similarly, we are having H22, which is output conductance, and it is denoted by HO. You remember that whenever we are taking any common configuration, such as suppose if we are taking common emitter configuration, in that case, this HI will become HIE. Okay. HR will become HRE, this HF will become HFE, HO will become HOE. To denote just to it is in the calculated in the common emitter configuration. Similarly, if it is common base or common collector, accordingly it will change like HIB, HRB, HFB, HOB. Okay, this way it will change. So this is the parameters that we have to calculate. So let's try to see how to calculate these parameters. So first of all, here you can see in the graphical procedure, this is the first parameter that we wish to calculate, HFE. Okay, so here you can see what is this HF. HF is the forward transfer current ratio. Okay, so forward transfer current ratio that we have to calculate, and normally this forward transfer current ratio will be actually calculated by this particular expressions. Okay, so here you can see here while calculating this H21, we have wrote V output should be equals to 0. But normally when we talk about the hybrid parameters in transistors, we take this V output will be corresponding to VCE in common emitter configuration, and normally it will be a constant value. It is not a 0. Okay, so here we have taken VC equals to constant. So normally before calculating the HFE using the graphical procedure, I have already discussed how to obtain the input and output characteristics of common emitter transistors. Okay, so please, those who have not watched that particular video, how to obtain the common emitter input output characteristics in common emitter configuration, please see those particular videos first, so that you will be able to understand. So here you can see that in the common emitter configuration, we have two characteristics. One is in the input loop and other one is in the output loop. So here in the output loop, we are having this output characteristics in common emitter configuration. And here you can see normally in this output characteristics, we are having collector to emitter voltage onto this particular axis. And here we are calculating the corresponding collector current. Okay, so here in the onto this y-axis, we are having the collector current. And this collector current set of this collector current will be calculated for a different set of values of your IB current. So here you can see this characteristics has been obtained for IB equals to 0 microamperes, 10 microamperes, 20, 30, and so on. Okay, so this way we have to keep this currents constant, and then we have to obtain this particular characteristics. So first we need to obtain this particular characteristics, and here you can see that normally when we calculate HFE, okay, we have to actually calculate this particular ratio. So what this ratio is, it is change in the collector current IC with respect to change in the base current IB, okay, while keeping the collector to emitter voltage should be a constant. So here you can see that where will be the collector to emitter voltage will be constant. So if you draw any vertical line, okay, if you draw any vertical line, because here we have this variation of the collector to emitter voltage. So if we draw any this particular vertical line, this vertical line will be corresponding to constant collector to emitter voltage. So let us say our operating point or Q point is equals to something this particular point. Okay, let us say this is our operating point. So here we have taken this example. Let us say at VC equals to 8.4 volt. Okay, let us say at 8.4 volt we wish to calculate what is the value of HFE. Okay, normally we have to calculate the HF in the active region. Okay, so it should be in the active region. We have to locate the Q point within the active region so that we will be able to calculate the HFE values. Okay, so suppose it is 8.4 volt. So first of all, we have to take this VCE equals to 4 volt, and then we have to choose a particular characteristics of this IC current for a corresponding value of IB. So here you can see at this particular value, we are taking a certain curve. Okay, so let us say this is our curve. So we are interested in this particular curve at 8.4 volt, where IB equals to plus 15 micro ampere. So here we can see that we have to actually calculate the variation in the delta IC. Okay, variation in the delta IC with respect to change in the delta IB. So here you can see what we have done is actually this variation in the delta IB is taken is equals to 20 minus 10 microamperes. So here you can see this is the curve corresponding to 20 microamperes, and here we have the curve, another curve equals to 10 microamperes. So this will become this vertical deviation in the, actually if you calculate this particular deviation, okay, this deviation will be giving you delta IC. Here you can see if we draw a dotted line like this at this point, first of all, we have to draw this vertical line. Okay, here we have the Q point. First, we have to locate the Q point. Then we have to choose a particular value of delta IB. So let us say this delta IB is corresponding to the 20 minus 10 microampere. So it is 10 microamperes deviation in the delta IB we are considering. So this particular line, if you see, this vertical line will be cutting this curve at this point. Okay, so at this point, this vertical line will cut this particular curve. Okay, this family of curve. So after getting this cross-sectional point, okay, at this particular point, this dotted line we have to draw. Okay, a perpendicular will be drawn onto this particular y-axis. So once you will draw this perpendicular to the y-axis, you will be able to calculate the delta IC. Okay. So this delta IC you can calculate from the curve, or if you have the observation table, from the observation table you can also calculate. So here we can see that this value is near about 2.7. Okay, 2.7 milliamperes, and here this current is almost equals to 1.7 milliamperes. So this way 2.7 minus 1.7 divided by 20 minus 10 microamperes. So how it is 20 minus 10? Because we are considering these 2 points. Okay. And these two blue curves are corresponding to IB equals to 20 microamperes and 10 microamperes. So delta IB will be becoming 10 microamperes, and then you can calculate this difference at a constant value of collector to emitter voltage. So this way, if you calculate, you will be getting this equals to 100. Similarly, if you wish to calculate the HOE, okay, so here you can see this two parameters. Basically, we have to calculate total 4 parameters. So out of 4 parameters, 2 will be calculated from the output characteristics, and another 2 will be calculated from the input characteristics. So this HOE is the this particular ratio. Okay, change in the collector current with respect to change in the collector to emitter voltage, while keeping this IB as a constant. So here you can see again, let us say this is the our IB. Okay, at a constant IB we have to calculate. So if we consider this is the Q point, fine. So what we have to do is you just you can try to draw a perpendicular, right? Again, you can just try to draw a perpendicular. Okay. So where is the perpendicular we have to draw? So first of all, you have to decide at what delta VC we have to calculate this value. So let us say this may be somewhere around in between 7 to 10 volts. So this is the midpoint, and from this midpoint you can choose equal deviation from of VCE. Okay, so here we have taken this at IB equals to plus 15 microampere curve. Onto this curve we have to choose this delta VCE. Okay, so this delta VCE we have taken as maximum as 10 and minimum as 7 volts. So any uniform deviation we have to take. Okay, this deviation should be in equal amount towards right side and the left side. Okay, it should be equal in amount. Okay, it should not be a different values. So here you can see if it is somewhere, if you take the average value of 10 and 10 plus 7 divided by 2, so it will be 17 divided by 2, so it will be around 8.5 volts. So this voltage is actually your 8.5 volt. Okay, so this VCE that we have taken at this point is VC equals to 8.5 volt, and then we have taken the deviation of plus 1.5 volt and minus 1.5 volt, and then this delta VC will become 3 volt. Fine. Similarly, so when it is at 10 volt, from this point we have to draw one perpendicular to this particular y-axis. Then at 7 volt again we have to draw another perpendicular. So this will give you delta IC, change in the delta IC. Okay, so this will be giving you delta IC. This delta IC you have to calculate. Okay, and here we will be getting this delta VC. Right, so this way you can calculate this ratio at IB equals to plus 15 microamperes. Remember that this constant value we have to choose as per our Q point, and we have to choose the Q point within the active region. That we have to take care. So here you can see this HOE, you will be getting something like 30 microsiemens. Okay. So this way you can calculate. You remember that hybrid parameters are not having uniform units. It is having a different units. Okay. Then similarly, you can calculate this HIE, okay, from the input characteristics. So this is our input characteristics. Here you can see that in the input characteristics, we are having base to emitter voltage drop onto the x-axis, and here we are having the base current, okay, in the microamperes order. So this curve is actually calculated for different values of VC. VC equals to 0 volt, VC equals to 10 volt, VC equals to 20 volt. Please go through my previous lectures, okay, in which I have already obtained these characteristics, okay. So here you can see this HIE is actually calculated delta VBE divided by delta IB. So it is the change in the base to emitter voltage if we are changing the base current. Okay, a small change in the base current, how much change in the base to emitter voltage will be obtained while keeping this collector to emitter voltage as a constant. So here you can see again how it can be graphically calculated. So here you can see this VC is taken as 8.4 volt. So here somewhere it is constant VC is taken as equals to 8.4 volt. So this curves are actually corresponding to different VCE. Okay. So here it is shown like with the black line, this black curve is actually corresponding to VC equals to 8.4 volt. This curve will be corresponding to 8.4 volt VCE. So from this curve, we have to actually locate the Q point, and then first of all, we have to choose what will be the deviation in the delta IB. Okay, so let us say this IB is equals to 15. So you just take the again equal uh, deviations, okay, from the 15 volts, so plus 5 microampere and minus 5 microamperes. So here you can see this will be giving you total delta IB. So this delta IB is equals to 10 microamperes, and while choosing this values of delta IB onto this particular curve, we have to again draw a perpendicular. Okay, so you just try to draw this small perpendicular line, okay, onto this particular x-axis. You will be able to calculate what will be the delta VB. This delta will VB will be very small value. Okay, you remember that it will be very small. So here you can get this delta VB. Here these values are already written. Okay, 733 minus 718. So you remember, first of all, you have to obtain this characteristic. Okay, without obtaining the characteristic, you cannot calculate the this parameters. Okay, this hybrid parameters cannot be calculated. First, you have to obtain the characteristics, then only you will be able to calculate. So this way, this ratio can be calculated. Again, you can see this HRE will be again calculated, and while calculating the HRE, this IB will be kept constant. Okay. So this IB should be constant. It should be constant, and then you can calculate what will be the deviation in the delta VVE with respect to deviation in the delta VC. This is what we have to calculate. Okay. So here we have the family of curves. So you can once you will drop this line, okay, it will be cutting the curve at two different points. So from this curve only, you have to calculate what will be the delta VC. So let us say this is corresponding to VC equals to 0, and this is corresponding to VC equals to 20 volt. So this delta VC will become 20 volt. Okay. And correspondingly, we have to calculate, you just drop this line to this x-axis, and here you will be able to see what will be the change in the delta VB. And this way you will be able to calculate what will be this ratio. So that ratio is coming out as 4 into 10 to the power minus 4. So this way you have to calculate these values, and later on these values you can write in this particular hybrid model. Okay, I have taken this typical parameters in common emitter, common collector, common base. Whatever I have explained is for the common emitter. Okay, you can similarly, you can also calculate the same thing using the other configurations, common collector, common base. Okay, so here you can see the typical parameters of the transistors. So now I'll be just going to the Excel sheet that I have already explained while getting this common emitter input characteristics and output characteristics. So here you can you must be remembering this particular experiment. So please go through that particular experiment. So this is the common emitter output characteristics of NPN transistor that we have already obtained. Here you can see that this characteristics is actually being obtained for constant values of IB. Okay. So here we have the IB equals to 0 microamperes, IB equals to 10, 20, 30, 40, and so on. We have to first get this curve. Okay. And after setting up this particular values of current, here you can see the experimental setup. Okay. This experimental setup, I have already explained how to conduct the experiment, how to obtain the input output characteristics. So that I have already explained. Okay. So you have to use the same setup again, and you can get this characteristics. So here I am just trying to show you how to calculate this HFE, okay, from the curve. So if you have already opted in this characteristics here, you can see I have just marked one of the value. Let us say that at VC equals to 7.5 volt, we want to calculate this HFE value. Okay, so here you can see at HFE equals to 7.5 corresponding to IB equals to 20 microamperes. So here you can see how many curves I have obtained. IB equals to 0, 10, 20, 30, 40, and 50. Okay. So here you can see this is 0, 10, and this is 20. So here it is a 20, IB equals to 20 microampere curve. Okay, this line is corresponding to IB equals to 20 microampere curve. And this value here you can note down, it is 7.5. Okay, this is VC equals to 7.5, and corresponding IB current is equals to your 6.431 that I have shown here as a yellow color. Okay, so at this Q point we can calculate what will be the value of HFE. So how it can be calculated? We have to take the equal deviation from the 7.5 volts. So here you can see I have taken 5 volt and 10 volt. So it is equal deviation from the 7.5 volt. Uh, sorry. So actually for calculating this VCE, uh, if you see this particular expression of the VCE, okay, we have already seen this. So here you can see this HFE. We have to take this VCE should be a constant value, right? So you have to take this VCE equals to constant. So this VCE should be a constant. So while calculating this current, okay, while calculating this HFE, you have to first take this constant value of VCE. So there should be a perpendicular, and then you have to calculate this changes in this current, okay, delta IC with respect to delta IB. So we have to change the delta IC and then we have to calculate the delta IB. So we have taken 20 microamperes, okay, and change in the delta IB. So basically we are talking about a curve corresponding to IB equals to 30 microamperes and then a curve corresponding to 10 microamperes, right? So here you can see this is 7.5, VC equals to 7.5. This all dots are corresponding to 7.5 volt of VCE, and this curve is corresponding to, here you can see, this is the third curve, okay. So it is corresponding to IB equals to 20 microamperes. This curve will be corresponding to 30 microamperes, and this is corresponding to 10 microamperes. This deviation, if you calculate in the VCE, it will be giving you delta VCE. And similarly, because it is 30 microamperes base current and it is 10 microamperes base current, it will be giving you 20 microamperes. So here you can calculate this deviation, right? You can calculate this deviation. I have written this delta IC. And this minus this, okay, 9.641 minus 3.124, it will be giving you delta IC, which is equal to 6.517. And similarly, delta IB will be 30 minus 10. It will be 20 microamperes. So here you can calculate this HFE as the ratio at a constant value of VC. Similarly, you can calculate the DVCE, delta VCE, equals to 5 volt. So when we changing the VCE, okay, from 5 to 10 volts. So this is 5, this is 10. Okay, we have to consider this to be a Q point 7.5, and then we have to take the equal deviation. So I'm just taking a deviation of 2.5 volt plus and minus 2.5 volt. So here you can take this total delta VCE will be equals to 10 minus 5 volt. It will become 5 volt. Okay. So it is 5 volt, you can see, and then we have to calculate this HOE again. So here you can see this HOE is the ratio of this delta IC upon delta VC at constant value of IB. Okay, so we have to talk about the constant value of IB. So constant value of IB means it is IB equals to 20 microamperes. So we have to consider this two values, okay, 6.237 and 6.626. These two values we have to choose, right? This will be giving you change in the delta IC. So that delta IC you have to calculate. This calculation might be a little bit wrong if you see, because here we have to take the delta IC. So here if you calculate the delta IC, you will be getting something else, because this delta IC is corresponding to this change, okay, 9.641 minus 3.126 is equals to this delta IC. But here the delta IC will be something different, okay. So you just try to calculate what will be this delta IC, okay. So this delta IC, we calculate the delta. So this value you will be might be getting is 6.626 minus 6.237. So if you subtract this value, let me turn on this calculator. Okay. So if you subtract these two values, you'll be getting how much it is 6.626 minus it is 6.237. Remember that we have to calculate this delta IC corresponding to constant value of IB. Okay, so and this value is coming out as 0.389. This value will be coming out as 0.389, and then you can substitute 0.389 milliamperes, you remember. Okay, so you have to substitute again to this particular formula of delta IC divided by the delta VC. So delta VC that we have taken is obviously it is. So this you can substitute in this expression. You will be able to calculate what will be the value of HOE. This way we have to actually make this. Again, this is our input characteristics, whatever I have explained there. Again, you have to do the similar calculation. For example, if you wish to calculate the HIE, okay, from the input characteristics. So we have to calculate the deviation in the base to emitter voltage with respect to change in the delta IB at constant VCE. So here you can see that we are having a different characteristics, okay, different VCE values, right? Different VCE values. So this curve is corresponding to constant VCE. So any constant VCE we have to choose. So let us say we are talking about VC equals to 10 micro, 10 volt. At this point, you can choose any value of VBE. So let us say it is 0.7 volt if we talk about. This is the Q point. Then you can choose what will be the value of delta VBE. So let us say if we take this immediate value 0.693 and 0.705, you can calculate what will be the deviation. So here you can calculate this deviations, right? What will be the deviation in the delta VB, and what will be the corresponding deviation in the IB current? Okay, that you can calculate from this two values. So it is 0.709, 705 minus 0.693. So that will be coming out as 0.012. And here you can calculate this 32.95 minus 23.1. That will be giving you 9.85. So here you can calculate this HI with respect to the constant value of VC. That will be coming out as 1.218 kilo ohms. Similarly, you can calculate this HRE. Okay. So hopefully HRE, while calculating this HRE, we have to keep this particular parameter constant. Okay. High B should be constant. This IB should be constant, right? So if you want to keep this IB should be constant, okay, here you can see this particular, any of one of the values of IB, okay, here you can see I have taken this IB 62.73, 62.72, 62.7. So while conducting the experiment, if you are specifically want to calculate the this hybrid parameters, so you have to remember that we have to get this constant currents. Okay, constant current you have to obtain. So obtain the constant current, and then accordingly you have to calculate the deviation in the this VBE and deviation in the VCE. Okay. So here you can see if we choose this VC equals to 20 volt curve and VC equals to 1 volt curve, even we can get the curve corresponding to VC equals to 0 volt. So here I have just taken VC equals to 20 volt and 1 volt. So this delta VC will become 19 volt. Okay, this delta VC will become 19 volt. And here you can see this IB current. Okay, delta, this IB current is constant 62.72, 62.73, 62.7. So corresponding value of this VB is equals to 0.73 at this point, and it is 0.727 at this point. So you have to just take the difference between the two. It will become 0.03 volt. Okay. So you can calculate this ratio. This ratio will be coming out as this value. So I hope you must be able to understand. So please follow this video and try to calculate the hybrid parameter using the graphical procedure. So remember that you have to first obtain this VI characteristics, and then you have to follow this particular explanation. So thank you for watching this video. If you have any doubt, let me know with your comments. Thank you.